Hi there, welcome back to Simplified Discrete Math for Computer Science. So for this session, we shall be diving into Boolean Algebra. Before we get started, I will share with you a quick overview of what will be discussed through the entire session. First of all, we shall have an introduction to Boolean Algebra. We shall later on understand the terminologies used. Then we shall learn about the Boolean Algebra operations, the Boolean Algebra laws, and the Boolean Algebra theorems. So we shall conclude the session with practice questions so that we grasp the concepts. Boolean Algebra is a mathematical system that deals with binary variables and binary logic operations. It was named after the mathematician and logician George Boole, who developed the algebraic system in the mid-19th century. Boolean Algebra is widely used in computer science, electronics, and digital circuit designs, where binary values of 0 and 1 are fundamental. So you realize that Boolean Algebra uses a binary system. So with the terminologies used in Boolean Algebra, one of them is a Boolean variable. A Boolean variable is a variable that can have one of two possible values, typically representing one of two binary conditions, either a true or false, but not both. Meaning that a Boolean variable either has a value that is true or a value that is false. So a variable is more like a container that is used to store data values. They can be numbers, characters, or strings. We shall look into variables later on in the future while handling the computer programming basics. A truth value represents a condition that is considered to be satisfied, while a false value represents a condition that is not satisfied. The other terminology is a Boolean expression. A Boolean expression is a mathematical expression or statement that evaluates to either true or false. It bases on logical relationships and operations involving Boolean variables. These terminologies move hand in hand. Boolean expressions are used to make decisions in control flow programs and also to evaluate conditions. An example of a Boolean expression is a into a plus b. We shall learn how to simplify these Boolean expressions, having learnt about the Boolean laws of algebra. Let's look at the components of a Boolean expression. A Boolean expression consists of Boolean variables, and these are variables that can have either a true value or a false value. For example, a and b can be Boolean variables. A Boolean expression also has logical operators that are used to combine or manipulate the Boolean variables. For example, we have the AND and the OR operators. A Boolean expression also has parentheses, which are brackets that we use to group and control the order of operations in complex Boolean expressions. So these parentheses are used to clarify the precedence of logical operations. We shall work with the associative law of Boolean algebra, where we shall see that Boolean variables can be grouped in a way that the grouping does not affect the final result. So before we start simplifying any Boolean algebra expression, we need to understand the Boolean algebra operations. So the first operation is the AND operation, which is also referred to as a conjunction. So it is represented using an inverted V, or it can be a period operator, or we can also use a multiplication symbol. So in a Boolean context, the AND operation is used to combine two or more conditions or variables, and the result is true only if both of the input values or the conditions are true. So if one of the values for any Boolean variable is false, the final result is always false. Alright, so let's have a look at a truth table for the AND operation. So for the truth table, we create a tabular representation of all possible combinations of the input values for a logical operation along with the corresponding output values. Alright, so for the truth table for the AND operation, we shall consider two Boolean variables a and b, such that we shall create a Boolean expression having a and b. So before we even start drawing the truth table, you have to take considerations on the number of rows. So for the number of rows, it's always 2 to the power n, where n is the total number of Boolean variables we are working with for the Boolean expression. So you can see that For this case, we are working with two Boolean variables a and b. So that means that our total number of rows is going to be 2 to the power 2, which is the same as 2 times 2, and this evaluates to 4. So while drawing the truth table for this Boolean expression, this is what we do. So we shall have our Boolean variables on the left, a, b, and then the Boolean expression on the right, a and b. So we consider cases whereby a is true and also b is true, and cases whereby a is true and b is false, then cases whereby a is false and b is true, and cases whereby or the Boolean variables are false. So this shows you that we are having 4 rows with the fact that we are working with two Boolean variables. So to simplify or to come up with a Boolean outputs for this Boolean expression, we know that cases whereby a and b are true, this will evaluate to true, and when a is true and b is false, this will evaluate to false, because we are using the AND operation, the logical AND. So when a is false and b is true, we shall have this as false, and when they are all false, this expression still evaluates to false. So this is the truth table for a Boolean expression of a and b. Alright, so let's look at the OR operation. The OR operation is also referred to as a disjunction. It is represented using the V symbol or the addition operator symbol, which is the plus. So in a disjunction, the result is true if at least one of the input values or the condition is true. So cases whereby all the values for the Boolean variables are false, then the final result for the Boolean expression is always false. So still we shall consider two Boolean variables a and b, and for the Boolean expression we shall have a or b. So take note of the operator for this OR operation. So still the number of rows will be 4, since we are only working with two Boolean variables. So for our truth table, we start with cases whereby a is true and b is true, meaning that our Boolean expression will evaluate to true. And cases whereby a is true and b is false, our expression will also evaluate to true. Then when a is false and b is true, the expression will still evaluate to true. And when they are all false, the expression will evaluate to false. Let's also look at the NOT operation. The NOT operation is also referred to as the negation. So in a negation, the result is always the opposite of the input value or the condition. So it finds the complement of the given Boolean variable. For example, the negation of a is true if a is false, and the negation of a is false if a is true. Alright, so let's look at the truth table for the NOT operation. So for this case, we shall consider a Boolean variable a such that the negation of a, which can be represented this way, or it can also be represented in this format. So the first thing we do is to consider the total number of rows we are going to work with. So the fact that we are only working with one Boolean variable, which is a, the total number of rows is going to be 2 to the power 1, which is the same as 2 times 1. So this evaluates to 2. Alright, so let's try drawing the truth table for this Boolean expression. So the variable we are working with is a, and its negation is going to be, can be a complement. So we shall consider the first case when a is true, and then the second case when a is false. So remember that for this expression, we are only working with a single Boolean variable, meaning that we are only having 2 rows. So cases whereby a is true, the negation of a is going to be false. And cases whereby a is false, its negation is going to be true. So meaning that you can pretty see that we are working with the opposite values for the Boolean variables. We're working with the negations. Simplifying of Boolean expressions will require one to be conversant and knowledgeable about the Boolean laws of algebra. So the first law we have is the identity law, where we consider 2 cases. One is the logical AND operation, where the presence of 1 in this operation has no effect on the final result. So that means that A and 1 always returns A. And for the logical OR operation, the presence of 0 in this operation has no effect on the result. So A or 0 will always return A. So meaning that A plus 0 will always return A. So the other law is the commutative law, where the order of the operands in a Boolean OR or a Boolean AND operation does not affect the result. So for the logical AND operation, you can have A and B, whereby it is the same as B and A. Then for the logical OR operation, you can have A or B, which is also equal to B or A. We also have the associative law, where the grouping of the operands within the OR operation and the AND operation can be changed without affecting the result. Alright, so let's look at the idempotent law. So with the idempotent law, applying either an AND operation or an OR operation to a Boolean variable with itself has no effect on the variable. So the result is always the same as the original value. So for a logical AND operation, A and A will always return A. And for the logical OR operation, A or A will always return A. The other law we have is the complement law, which describes the relationship between a variable and its complement. In other words, the relationship between the variable and its negation. So for the logical AND operation, the result of performing a logical AND operation between a variable A and its complement is always equal to false. And then for the logical OR operation, the result of performing this operation between a variable A and its complement is always true. The other law is the distributive law, which relates to binary operations, often addition and multiplication. We have the left distributive law, where multiplication distributes over addition, and the right distributive law, where addition distributes over multiplication. So with the distributive law, it's more like opening of brackets such that we perform the Boolean algebra operations, and also to simplify the expression furthermore. So let's look at the absorption law. The absorption law describes how certain binary operations interact with each other. We have the left absorption law and the right absorption law. With the left absorption law, for any elements A and B, the result of performing addition on A and the product of A and B will simply return into A. And for the right absorption law, for any elements A and B, the result of performing multiplication on A and the sum of A and B is also A. Here is a quick overview of the other laws that we shall be working with time. We have the annulment law, the redundancy law, the De Morgan's laws of theorem, and very other many laws as they are listed. We can only learn these concepts through practicing them. So let's have a look at some problem sets for Boolean algebra. For problem set 1, we shall be simplifying the following Boolean expressions. So for this Boolean expression, we have z into y plus z into x plus y plus z. So even before we proceed, we can see that we are having two laws that are already used. So the first law we have is the left distributive law, which is being applied here, where we are having z into y plus z, meaning that multiplication is being distributed over addition, because this z is going to be multiplied by y plus z. And secondly, we are also having the associative law, because we are having y plus z being grouped, and we are also having x plus y plus z. So to simplify this Boolean expression, we are going to simplify it from the left, meaning that we are going to start with the left distributive law. So we are going to open brackets, where we shall have z being multiplied into y plus z. So this will be zy plus zz. Then we combine it with the associative law, meaning that we group these Boolean variables into x plus y plus z. So we know that z multiplied by z will always return z, and this is the idempotent law. So this is the same as zy plus z into x plus y plus z. So we can see that now for this case we are going to use the right distributive law, where we are having addition being distributed over multiplication. So that means that we are going to have xy being multiplied into this bracket, and we are also going to have z being multiplied into this other bracket. So this will be zy x plus zy y plus zy z, then plus zx plus zy plus zz. So a quick reminder, we know that still the idempotent law is being used for this case where we are having y and zz. So this will be zy x plus zy plus zyz plus zx plus zy plus z. So for this case, we can now check out for common Boolean variables. So we can see that on the left hand side we are having zy and zy common, and then on this other side we are having z and z common. So we pull out the common Boolean variables. So we shall have zy into x plus 1 plus zy z plus zx. Z is the common variable for this. So z into y plus 1. So we know that the annulment law states that x plus 1 will always return 1, and also any Boolean variable for the operation with 1 is the same thing. So this will always return 1, so meaning that y plus 1 will also return 1. So this is the same as zy plus zyz plus zx plus z. So we can see that on this case, zy is common here and zy is also common here. And on this other side, we are having z and z common. So we pull out the common variables. So zy into 1 plus z plus z into x plus 1. So we can see that on both sides we are having the annulment law, so meaning that the output of this is going to be 1. So this is the same as z multiplied by 1 plus z multiplied by 1. So we know that any Boolean variable multiplied by 1 will always return the same Boolean variable. So this will be zy plus z. And we can see that z is common for this expression, so we pull it out, z into y plus 1. Until the annulment law is being used here, so this will be z multiplied by 1, which will evaluate to z. So we can say that the Boolean expression evaluates to z. Alright, so let's look at the second Boolean expression. We are having xyz plus xyzw plus xz. So for this expression, you can see that no Boolean law has been applied. So the first thing we are supposed to do is to check out for the common Boolean variables. So from left, you can see that xyz is common here and xyz is also common here. So we have to pull out the common Boolean variables. So we shall have xyz into 1 plus w, then plus xz. So we know that 1 plus w will always be 1 according to the annulment law. So that means that we are going to have xyz multiplied by 1 plus xz. So any number multiplied by 1 will always return the same number. So this will be the same Boolean variable xyz plus xz. So for this expression, we have to still pull out the common Boolean variable. So we can see that xz is common here and here. So we pull it out. This will be xz into y because y is the only variable that has been left here. So this will be y plus 1. And still the annulment law is valid for this case. So we shall have xz multiplied by 1. And this will result into xz. So we can say that this Boolean expression evaluates to xz, hence simplified. Alright, so for the third Boolean expression, we have a plus b in two brackets, then plus b complement. So first of all, we can see that a plus b has been grouped, and this is the associative law. So what we do, we open the brackets, so we shall say a plus b complement. So a quick reminder, we know that the complement law states that b plus b complement is equal to 1. And this applies for the OR operation. And we also know that b multiplied by b complement for the AND operation evaluates to 0. So for this case, we are going to consider this. So we shall substitute this. So we shall say a plus 1. And we know that the annulment law says that a plus 1 will always equate to 1. So this is the annulment law, and this is the complement law. Alright, so this will be 1. So we can see that our Boolean expression evaluates to 1, hence simplified. Alright, so let's look at the fourth Boolean expression. So we are having AA plus BC complement. So we can see that AA is the idempotent law, where we know that any Boolean variable multiplied against the same Boolean variable for the AND operation will always return the same Boolean variable. And this also cuts across for the OR operation. So this will be A. So to simplify this, we shall say A plus BC plus BC complement. So on this step, we now have to check out for the common Boolean variables, and see that B is common here and here. So this will be A plus B. So we pull out the common Boolean variable. So this will be C plus C complement. Alright, so we also know that the complement law states that C plus C complement for the OR operation will always return 1. And we also know that C complement for the AND operation will always return 0. So for this case, we are going to apply this law here. So this will be A plus B multiplied by 1, and you know that any number multiplied by itself will always return the same number. So this Boolean variable will still evaluate to B. So this will be A plus B. So hence the Boolean expression evaluates to A plus B. So to note this down, this is the complement law and this is the idempotent law. For the fifth Boolean expression, we are having A complement plus C plus AB. For this expression, the first thing we have to do is to rearrange the Boolean variables, because we can see that there aren't any common variables. So we shall say A complement plus AB plus C. So we know that the redundancy law states that XY complement plus Y will always return X plus Y. And this is true for X complement plus XY, which will evaluate to X complement plus Y. So for this case, we can see that we can apply this law here. So meaning that we are going to be applying this law, the second one, for the redundancy law. So this will be simplified into A complement plus B plus C. So we can see that we cannot simplify this Boolean expression furthermore. So hence, therefore, it evaluates to A complement plus B plus C. Hence, simplified. So for Boolean expression 6, we are having A complement into B plus AC. So we can see that we are having the left distributive law for this case, whereby A complement will be distributed over B plus AC. So this is the left distributive law. So we shall simplify this into A complement B plus A complement AC. So to remind ourselves about the complement law for the AND operation, we know that A complement A will always evaluate to 0. So meaning that this expression is going to evaluate to 0, because any number multiplied by 0 is going to be 0, because 0 is going to be multiplied by C. So we shall have A complement B plus 0. So this will evaluate to A complement B. So we can say that this expression evaluates to A complement B. So take note that this was the complement law. Well, so let's have a look at problem set 2. Alright, so for this Boolean expression, we can see that BC is common here and here. And we can also see that BC complement is common here and here. So what we are going to do, we are going to follow the commutative law such that we rearrange the Boolean variables, because we know that the order of the operands does not affect the final output. So we shall say A complement BC plus A BC plus A BC complement plus A BC complement plus A B complement C. So for this expression, you can now see that we can remove the common variables, which is BC. So we shall say BC into A complement plus A, then plus BC complement into, because BC complement is the common variables. So we shall remain with A plus A complement plus A B complement C. So we can see that this and this have been grouped. A complement plus A and A plus A complement have also been grouped according to the associative law. So on this, note that A complement plus A will always be equal to 1, and this is also true for A plus A complement being equaling to 1. And you know that this is the complement law for the OR operation. Alright, so we shall have BC multiplied by 1 plus BC complement multiplied by 1 plus A B complement C. So this will equate to BC plus BC complement plus A B complement then C. According to De Morgan's law of theorem, BC complement is the same as B complement plus C complement. So we are going to substitute this BC complement with B complement plus C complement. So we shall have BC plus B complement plus C complement plus A B complement C. So we have BC plus B complement plus C complement plus A B complement C. So at this point, we can now see that BC plus B complement follow the redundancy law. Well, we know that B complement plus BC is the same as B complement plus C, and this is the redundancy law. So we shall have B complement plus C plus C complement plus AB complement C. So we know that C plus C complement evaluates to 1 according to the complement law for the OR operation. So we are going to have B complement plus 1 plus A B complement C. So we know that the annulment law states that B plus 1 will always equate to 1. So this is the annulment law. So we shall substitute 1 plus A B C. So still according to the annulment law, 1 plus any Boolean variable will always evaluate to 1. So hence the Boolean expression simplifies to 1. Alright, so let's look at the second Boolean expression. So for this Boolean expression, we can see that AB plus C is following the associative law of grouping the Boolean variables. So we can use the left distributive law in a way that we multiply ABC into this brackets. So we shall have AB plus SC complement plus AB complement C, AB plus AB complement C, C. So for this step, we know that this A complement A will always equate to 0 according to the complement law for the AND operation. And we also know that C multiplied by C will always evaluate to C according to the idempotent law. So we simplify this by AB plus SC complement. So plus 0 then means that we shall bring in the last Boolean expression. So plus A B complement C. So we also know that according to De Morgan's law of theorem, SC complement is the same as A complement plus C complement. So meaning that for this part we substitute it with A complement plus C complement. So we shall have AB plus A complement plus C complement plus A B complement then C. So furthermore, we can see that we are having the redundancy law here. So we shall have B plus A complement plus C complement plus A B complement. So when you try to rearrange, you can see that we can rearrange this with B and then A B complement C. So we shall have B plus A B complement C plus A complement plus C complement. So still according to the redundancy law, we know that we shall have B plus SC plus A complement plus C complement. So we can also rearrange this. So we also know that we can apply the redundancy law here. So we shall have B plus C plus A complement plus C complement. So when you try to rearrange, you can have B plus C complement plus A complement. So we know that C plus C complement will always evaluate to 1 according to the complement law for the OR operation. So we shall have B plus 1 plus A complement. So we know that B plus 1 according to the annulment law for the OR operation will always evaluate to 1. So this will be 1 plus, so we shall have 1 plus A complement. and this will evaluate to 1. So we can see that this Boolean expression also evaluates to 1. So for Boolean expression 3, we are going to follow the distributive law, because we can see that these Boolean variables have been grouped according to the associative law. So we shall have this bracket being multiplied over the other bracket. So we shall have AA plus AD plus CA plus CD. So A multiplied by A will always result into A according to the idempotent law. So we shall have A plus AD plus CA plus CD. So we can see that A is common here and here. So we pull out the common variable A, which is A into 1 plus D. Then plus, we can also see that CA is common, but for this case we can keep it simple for now and say CA plus CD. So 1 plus D we always evaluate into 1 according to the annulment law for the OR operation. So this will be A plus CA plus CD. So we can see that A is also common here and here, so we pull it out, A into 1 plus C plus CD. So still this will evaluate to 1 and we shall have A plus C. Hence this Boolean expression evaluates to A plus C because we cannot simplify it furthermore. Alright, so for the fourth Boolean expression we can say that B complement C is common here and B complement C is also common here, and we are having BC complement common here and here. So we are going to pull out the common Boolean variables. So we shall have B complement C into A plus A complement plus BC complement into A complement plus A. So A plus A complement and A complement plus 1 will evaluate to 1 according to the complement law for the OR operation. So we shall have B complement C plus B C complement. So for this case we can see that B complement is common here and here, so we shall pull it out, B complement into C plus C complement. So C plus C complement will evaluate to 1 and we shall have B multiplied by 1 and this will evaluate to B complement. So hence the Boolean expression can not be furthermore simplified. So for this Boolean expression we are having A complement plus B multiplied by B complement plus C. So we shall first of all open the brackets based on the distributive law. So this will be A complement B complement plus A complement C plus B complement plus B C. So we can see that B times B complement will always evaluate to 0 according to the complement law for the AND operation. So we shall have AB complement plus A complement C plus, of course this is 0, so we shall have B C. So according to De Morgan's law of theorem, we know that AB complement will always be A complement plus B complement, then plus A complement C plus B C. So when we try to arrange these Boolean variables, we shall have A complement plus A complement C plus B complement plus B C. So A complement is common here and here, so we shall pull it out, A complement into 1 plus C plus B complement plus B C. So we know that 1 plus C will evaluate to 1 according to the annulment law for the OR operation. So we shall have A complement plus B complement plus B C. So we can see that B complement plus BC follows the redundancy law. So we shall have A complement plus B complement plus C. So we can see that this expression cannot be simplified furthermore. So that means that it be simplified to this. So for part 6, we have AC plus AD plus ACD complement plus AB. So we can see that CD complement can be simplified using the De Morgan's law of theorem. So we shall have SC plus AD plus A into C complement plus D complement plus AB. So this will be SC plus AD plus, so we open the brackets, SC complement plus AD complement plus AB. So we can try to rearrange this basing on the commutative law. SC plus AC complement plus AD plus AD complement plus AB. So we can pull out A since it is common here. C plus C complement plus, we can also pull out A, and we have A into D plus D complement plus AB. So C plus C complement and D plus D complement will evaluate to 1. So we shall have A plus AB. So A plus A will evaluate to A according to the idempotent law for the OR operation plus A, B. So we can see that A is common, so we shall pull it out and have A into 1 plus B. And we know that 1 plus B will evaluate to 1 according to the annulment law for the OR operation. So we shall have A, so hence the Boolean expression evaluates to A, and we cannot simplify it furthermore. So for part 7, we shall simplify this by saying A complement plus C complement into A complement plus B complement. So we shall have A complement plus, so we know that C complement follows the double complement law. So we shall have C, because we know that double complement of a Boolean variable evaluates to the Boolean variable, into A, same law here, plus B complement. So this will be A, we are opening the brackets, plus A complement, B complement, plus C, A plus C, B complement. So we know that A complement, A will evaluate to 0 according to the complement law for the AND operation. So we shall have A, B complement plus CA plus C, B complement. And according to De Morgan's law of theorem, we know that AB complement evaluates to A complement plus B complement plus then CA plus CB complement. So when you try to arrange this, A complement plus CA, we shall have A complement plus C, then plus B complement plus CB complement. So we know that B complement is common here and here, so we shall have A complement plus C plus B complement into 1 plus C. So we shall have A complement plus C plus, so we know that 1 plus C will evaluate to 1, so we shall have B complement. So this is the same as A complement plus B complement plus C. And we know that A complement plus B complement is the same as having AB complement plus C. Hence simplified. I hope you found this session informative. Thanks for watching and see you again in the proposition logic session.